Hello and welcome to Lab 3, Black Holes and Orbits. I'm Joe Giuliano and I'll be presenting to you today. So here's the introduction. For this lab, we used only Glowscript and we modeled Newton's law of universal gravitation. So the purpose of this lab was to model the law of universal gravitation using computational models and to understand this law. So in part one of the lab, we found that the mass of the black hole to be 1.2 times 10 to the 34 kilograms. And in part two, we created a model that shows a spaceship orbiting both the moon and a planet. However, it was impossible to make the spaceship orbit both as a figure eight. And here are our principles that we used. We used Newton's second law, universal gravitation, and net force. And for our models, we used two Glowscript computational models, our first one being a black hole and the second one being the double orbit model. And so here are the equations we used. So the first one is Fg equals gmm over r squared times r hat, which is our law of universal gravitation. We have our second formula, which is the position update formula here, which we've used in previous labs, and velocity update formula, which it was also used in previous labs. For our overview, we have the black hole mass for part one. So our goal here was to find the mass of black hole given starting code, and with an object moving in an elliptical orbit around the black hole. We were also given a random elliptical orbit based on our emails used as a seed for the starting code. And for part two, our goal was to orbit and not crash into the moon or the planet while we were orbiting, while also trying to create a figure eight orbit. So for our initial conditions, so we have the email here, which was our seed for the elliptical orbit. We have the gravitational constant, the mass of the star, and our delta t, which is the time step, which is every 86,400 seconds, which is 1 Earth day. And then we have our masses and constants here. We have, for part two, we have our gravitational constant, we have the planet's mass, the moon's mass, the ship's mass, our time step of 60 seconds, and then our speeds for the ship. So we have negative 16,000 meters per second in the x direction and 38,000 meters per second in the y direction. And so these were modified to model our figure eight orbit as close as possible. And we also, for our initial conditions, we had the spaceship initial position on the surface of the moon. So here's our experiment code for part one. We have the massive black hole code here, which was calculated by rearranging the equation for the universal law of gravitation. And again, our resulting value after taking the average of each different value given for the massive black hole due to it changing in our calculation was approximately 1.2 times 10 to the 34th kilograms. And here's our calculation loop on the right. For part two, we have our force calculations on the left, which is the planet to moon, ship to moon, planet to ship, and moon to ship net force calculations. And then we have our Newton's second law calculations to calculate the moon's velocity in position and the ship's velocity in position during part two. And here are videos for each model. This is part one. So we have the elliptical orbit here. And as you can see, it speeds up around the center and it's slower on the outside. And for part two, as you can see, there's a slight figure eight orbit right here, but it's not maintained throughout the entire orbit. So for our what if you had a four-body system of the black hole, the star, the planet, and the moon, the net force on each body would have to be calculated like we did in part two. The dominant interactions would be between the body with the greatest magnitude and the body with the least magnitude, as those would have the biggest attraction force to the body with the greatest mass. And for what does it mean? So the net force and the parallel and perpendicular components of the change of momentum are the same. However, net force needs to be calculated by finding all the forces applied to the system, whereas the rate of change of momentum can be calculated using the momentum formula over change in time, which is P equals mv divided by delta t. And to conclude, we had our part one, which we used universal gravitation to find our mass of the black hole, given our random elliptical orbit. And in part two, we had our figure eight orbit, which we were able to partially model, but not fully model, as it's impossible in this case to maintain a figure eight orbit due to the planet having much more mass than the moon, and therefore proportionally much more gravitational force acting on the ship. And for our assumptions and sources of error, we assume that the net force in part 1 is only due to the black hole at the origin, and we assume that 1 day equals the time for Earth to make 1 revolution around its own axis as delta t. And for our sources of error, we have the different interpretations of the figure 8 orbits, possible incorrect coding calculations, different ellipses for each lab, and possible incorrect initial spaceship velocity. And that's it. Thank you.